Okay, let's see what we got here. Smallest integer divisible by k. Given a positive integer k, you need to find the length of the smallest possible integer n such that n is divisible by k. The length of the smallest such that n is divisible by k and n only contains digit 1. Return the length of n. If there is no such length, return -1. If n may not fit in a 64 signed integer. Okay. What's the size of k, I guess? Divisible by something that is up to 10 to the 5th. Needs to be all ones. So k is 2. 2 is never going to be divisible into something, or something with all ones is never going to be divisible by 2 because it's odd. Guess maybe I could make, so k has to be even. Otherwise it's going to be an odd number divided by an even number, which means it's never divisible. So I guess I can possibly do it. A trivial case. If k is odd or is even, not possible. And maybe, I think if k is odd, then it's going to be always possible. Can't imagine it not being possible if it's odd. Because eventually you'll get something with, okay, not sure. If k is odd, so k mod 2 is 1. No, k is even. Then return -1. Okay, I think that's the only impossible case. So I have to go about the possible case. It's going to test my number theory knowledge here. So if you have a number that's all ones, you probably don't want to actually simulate it. Like, you don't want to actually generate the number, particularly because it can be like a lot of bits or very large number. But if you don't simulate it, if you don't actually construct the number that's all ones, can you somehow, what operation do you perform? Number theory. Huh. So let's see. Let's take a random example. Let's say case. I think maybe I can I guess the worst case is k is like a pretty large prime number, because then I can't even use maybe some sort of decomposition of k or factorization of k to simplify the calculation. So let's say it's like a, pretty sure like 113 is a prime number. Because, yeah, sure. So let's say 113 is prime. Well, let's not say that. 113 is prime. And what would be the earliest number of ones that is divisible by 113? So not 1, obviously it has to be at least 113, so the earliest one could be 4 ones. I guess what I'm thinking about is, how do you relate maybe a number that has p bits that are all 1 versus a number that is p plus 1 bits that are 1s. If there was a relation there, then there could be some sort of calculation that is incremental. Okay, so let's say 111 mod 113. What is that? $94. And then 1111 mod 113 is 37. So eventually it needs to be 0. Okay. I wonder if it's cyclic. Like the difference between 94 and 37 is maybe some value. 94 minus 37 could be cyclic. I mean, it has to be cyclic, but is it the same cyclic difference? 57. I should probably have been able to do that in my head. So then it's 37 minus 57, which is negative 20 in 113. It's going to be 80. This is unlikely to hit. It's unlikely. It would be like 90. 113 minus 20 would be. Is it 113 minus 20 or 112 minus 20? Might be 112 minus 20. 0 is 113. I think it's 113 minus 20, so it'd be 93. Maybe. I doubt this is the pattern. Or I doubt this pattern holds. 32. Yeah. It's just the way the numbers are increasing from 1000 from this 4 ones to 5 ones to 6 ones is not really a constant difference. So therefore I don't think the cyclic remainder is going to be constant. Cyclic being numbers that are between 0 and 112 inclusive, because those are the only possible remainders. It has to cycle through it has to, well, obviously the remainder has to be somewhere in there, but doesn't necessarily have to exactly cycle once through every value. It's like increase the number of ones. Okay, so let's see if I can spot a pattern though. Or not a pattern per se, but some way of figuring out how to format the calculation. Interesting. I think here, so if you have, let's say, a value v mod 113, and let's say that gives you an r value, and then you take v plus 1, that would be 10 times v plus 1 mod 113. Times v plus 1. I think that should be equivalent to doing 10v mod 113 plus 1. Mod 113 is just going to be 1. So is that correct? Is 1110 mod 113 equal to 36? 110. 4 ones, I think it's 4 ones, right? 4 ones and a I want to do 4 ones. So why did that not give me 1110 mod? Oh. No. It's 36, yeah. Okay. So I think that's mathematically correct. Okay. 10b plus 1. Well, so if 4 ones mod 113 is 94. So if I do 10 times this, so we'd have to do the same thing as 94. Yeah, I think it'd be 94 times 10. So it's 940. 940 plus, so 941. 941 mod 113 is 37. Okay. So I can, okay, so the calculation just boils down to you take your value, mod your k, get a remainder, then you do 10 times the remainder plus 1 until this is eventually 0. Okay, it might not be fast enough, but it's something. So while the remainder, I guess your initial remainder should be, whatever, I guess your initial remainder is 1, right? Yeah, so let's say n is the number of ones. Okay, so let's say the count, so the answer was initially 1 bit. The remainder is originally 1, because that's the same thing as 1. Then while the remainder doesn't equal 0, then the answer increments. It's going up 1 extra bit, an extra 1, not a bit, 1 extra digit of 1. Then your remainder should be your remainder is initially 1, right? If this is base, it's only 1. If k is not equal to 1. Otherwise, there's always going to be a remainder 1. Yeah. Remainder equals 10 times previous remainder mod k plus 1. I think that's it. Unless there hits the impossible case. It's timing out. K is 3. Oh, it's 3. It's timing out on which one? K is even, it's not possible. say for answer equals 10. Let's go and print out what case this is, that it's going past bar. Let's go to timing out on something earlier than that. Why would it time out k? Oh, well, timing out k equals 3. The remainder is 1. The answer is incrementing. The answer should eventually hit 10. Oh, this is OR. Okay. While the remainder doesn't equal 0. So case 3, the remainder starts with 1. 1 divided by 3 is 1 divided by 3 has a remainder of 1. Then your remainder is going to be 10 plus 10 times 1. 10 plus 1 is 1 times 10 is 10. 10 mod 3 is 1. 1 plus 1 is 2. Let's go ahead and just print out what these values are. What is the what is it calculating? 2, 3. What the hell is this? Oh, mother lord. Oh my god. I'm so stupid. Yep. I'm so stupid. Okay. Can I get rid of the extra bits here? Yeah, I can't out. Obviously, the remainder is never going to be 0. So I'm going to add 1 at the very end. I guess I could also do while the remainder dot not equal to k. I guess that's equivalent. It's all the same. So not you add 1 right after. Yeah, it's the same. So might be too slow. Where's timing out? Interesting. This is impossible, isn't it? Yeah. Definitely impossible. I guess if you're... How do you detect if it's impossible? I think if it's impossible, if there's some sort of pattern. Is 5 the only thing that's impossible? I guess it's 5 or number divisible by 5, maybe? K mod 2 or K mod 5. I think that might be it, right? Is that right? I feel like everything else should probably work. things in base 10, those are the only things that are divisible in base 10. Okay. I should have caught that one maybe, if I thought a little harder about just the very simple test cases. Alright, whatever. I'm good. So yeah, so I think maybe I'll keep the small bits of work here. So in summary, this is more of a number theory type problem, with some minor bits of kind of computation, algorithmic computation. Mainly this requires noticing how calculation of the remainder can be incrementally computed based incrementally computed, for example. I guess this be i.e. how the remainder of a n digit number of ones is related to the remainder for a n plus 1 digit number of ones. Okay. So can look at the above notes / work, but in essence can use just the remainder times 10 plus 1, obviously on modulo k, to find the next remainder, and then use the whole number with all the ones. This is because in the modulo number system, the numbers are equivalent if their remainders are the same. So for example, both in say mod 3, something that has remainder 2, which is like 5 and 8, which are both equivalent to 2, basically. 2, 5, and 8 are all remainder 2, so therefore they're all equivalent. So you can, instead of using the long n digit number, you can just use the remainder value to substitute for the next calculation. Time complexity O of, how slow is this? It's pretty fast, I guess. Actually don't know. Actually, am unsure about this. Should be fairly fast, considering that the calculated value is going up by a factor of 10 each time. So if the maximum k value is, so I'm going to guess something like O of log k, maybe. Space complexity, let's give me O of 1, since no extra space is needed. There's some other stuff in terms of like having a solution that take into account the impossible cases or